My name is Mansoor, and I work at University of Southeastern Norway, Westfold campus. I'm working there as a postdoc with the Institute of Microsystems. This brief presentation, I will be talking with you about the equivalent circuit model for a hybrid transducer that is capable of operating at distinct frequency ranges, given that both the architectures share the same footprint. So the plan is to give you a historic. I'll start with giving you a historic overview of some of the key developments that we have seen in this hybrid ultrasound transducers and the acoustic performance that has been shared back in 2018 on in ultrasound symposium for the first single element T-hat, and the effect of the coupling between these two transducers, the low frequency and the high frequency. High frequency consists of CMOS, and the low frequency is the PZT resonators with matching layers. So what is the effect of low frequency stack on high frequency CMOS bandwidth? I'll talk about that. Then why the question about why we prefer these analytic models instead of PAMs to characterize and predict the behavior of T-hats. I'll briefly talk about that. What are the advantages of using circuits instead of PAMs? And not only that, we can predict the behavior of the hybrid transducer with circuit models. We can also use them to investigate the design of CMOS arrays to match the required, let's say, bandwidth and the receive performance. So to start with, let's quickly recall the principal operation of a CMOS receiver. Since the high frequency part consists of an array of CMOS cells, this is a cross section of a single CMOS cell, which is in which you see the electrodes are biased externally. This establishes an electric field given in the direction of the polarity. So when the incoming ultrasound or the mechanical disturbance hits the front plate, the top electrode, which is free to move under the influence of this mechanical disturbance, the plate vibrates, and this vibration causes the change in the capacitance, which is established by the field. This change in capacitance results in the alternating voltage signal, which is then taken up by the interfacing electronics. It could be a low noise voltage preamplifier or a transconductance amplifier if the current input is required. Then that is taken up further for digital processing, signal processing for image formation in console. So that's the basic operation of a receiver. So if the same transducer is to be configured, for example, as a transmitter, then you apply a harmonic signal between the two electrodes, then the top electrode vibrates and pushes the medium back and forth, generating ultrasound in the medium. Okay, so that's the basic principle. So some of the advantages of CMOS are according to the architecture of CMOS, they are inherently low-Q devices, which translates into very wide bandwidth response, which also means that very good time resolution when it comes to image formation. CMOS can achieve coupling conditions close to 100% if membrane is biased close to the collapse as compared to the counterparts of piezo ceramic transducers. CMOS are manufactured using photolithography process, standard IC-based processes. So whatever you can write for on a chrome mask used for photolithography, I mean, you can make those arbitrary shape and size membranes. I mean, there's no limit to the array geometries. It can be a polygon, square, or circular, whatever. So, in fact, whatever you can write with a mask, you can realize it in a clean room environment. So CMOS are also suitable for high frequency applications. The frequency of CMOS, unlike piezo's, are tunable with applied voltage actually. As you go on increasing the voltage, unless the membrane is not collapsed, only the spring softening effect, you can tune the voltage of the frequency of CMOS. CMOS are more amenable, open for with interfacing electronics. So in small, they can be integrated with electronic circuit in chip scale packages, enabling miniaturization, leading to small form factors and more reliable and robust designs. Here is a single element prototype of a hybrid transducer that was first introduced back in 2018 in iOS. You can see that there is a single element CMOS that is bonded on top of a PZT having a quarter wavelength matching layer, and then there is a soft backing with alumina and tungsten filled material. The idea is that this given transducer is capable of operating at distinct frequency bands, and this proposed hybrid approach has been seen to be can be conveniently be used in nonlinear ultrasound imaging, like tissue harmonic imaging. So the key requirement for distinct frequency operation is fulfilled by a linear large signal transmit. So PZT is a linear transmitter, while CMAT over here is a wideband echo receiver. The acoustic performance that was done for this hybrid architecture consisted of both the electrical impedance measurements and the transmit and receive performance of the D hat. So you can see on the left side we have the pure CMAT element, which operates at around 20 megahertz. Although the voltage is varied from 0 to 260 volts. There's not much of a spring softening effect that can be seen in a D hat array for the pure CMAT element. But however, it doesn't mean the coupling conditions don't change. They do change drastically. The figure on the right is the hybrid architecture, in which there is a resonant backing consisting of PZT and the low frequency stacks of matching layers and dematching layers. So you see that you have this the first thickness mode resonance of PZT appears around 7 megahertz. So you see the impedance levels are much smaller than CMOS, primarily due to CMOS. I mean, the way the structures are, they're predominantly capacitive, and the impedance levels are much larger than those of PZT. So it's zoomed in to show that these two peaks relevant to the underlying stack of PZT. And you see the third mode of frequency of PZT around 22 megahertz, and which is also seen in the reactive part. So that's how you have two distinct frequencies for these transducers. Now, to design these transducer FEM simulations were previously used to study the behavior of transducer, and they were adopted to fabricate and predict the behavior of the T-hat. So as far as single element goes, FEM's predictions are numerical predictions are very accurate, and it was actually done back in 2016. These characterizations was done in 2018. So, but when it comes to the simulating large number of CMOS cells, the FEM can be computationally very intensive, and then you have to assume periodic boundary conditions, and these periodic boundary conditions can sometimes ignore some of the nonlinear effects like mutual crosstalk within CMOS elements and coupling with the lower frequency stack. I'll talk more about it in a while. So the other thing is the acoustic measurements of the single element T hat, and as you can see, there are two things to notice over here. For the low frequency stack, the two pictures A and B shown on the left, as can be seen, the peak, transmit, and receive sensitivity of the PZT is not affected by the CMOS mounted on top of it. You can see the peak sensitivities are not much affected, neither the bandwidth of operation. But around 7 megahertz, it's about the same. It doesn't matter. But it's not the other way around for CMOS. If the pure CMOS element is considered, the pulse echo measurements reveal that the CMOS is very, very clean, very wide bandwidth. But when it comes to characterize the hybrid architecture, CMOS having resonant backing, then the bandwidth at 14 megahertz is limited to 70% as compared to as compared to normally what CMOS are known for. I mean, CMOS can achieve bandwidth more than 100% if while operating at very close to the collapse condition or 100% coupling conditions. So those are the advantages of CMOS. But in this particular configuration, what was revealed is that the bandwidth is severely limited by the underlying PZT stack. Although there has been some efforts reported in the literature. For example, researchers have introduced interlaced or interleaved architectures in which the two transducers don't share the same footprint, so you don't have this coupling over there. But if it's the same footprint, it can still be reduced by using materials like silicone or RTV rubber, in which, because of the attenuation, the peaks they go down a bit, and then they're also shifted down in the frequency, affording more bandwidth. So there is some effort that has been done in this group by some of the people in this group, and I've seen that how to reduce this problem. So, well, now given the success of single element D hat, the idea is to move on to a 1D array of a CMOT. So I'll start with the linear circuit model of a CMOT cell, which can predict the behavior as good as FAMS. So the linear circuit model of a CMOT cell can work up to the accuracy of finite element model level. They have shorter simulation times, and they can handle absorbing boundary conditions easily due to the analytic nature. So there are a set of equations which we have to solve. For example, the lumped components. Each and every lumped component is defined in terms of the circuit, the CMOS dimensional and physical properties, and it can be solved by any available, let's say, a commercial circuit simulator. So it doesn't take much time to simulate when it comes to the large CMOS cells, and you can, instead of assuming periodic boundary conditions, you can simulate the entire array. Doesn't matter, 100 cells, 1,000 cells within a short period of time. So they're also suitable for design optimization in sensors. For example, what happens if you go for thin membranes, or what is the effect of larger aperture sizes on the bandwidth of CMOS, things like those. So it can also be used as a design. I'll give some examples on how it can be designed using these circuit models. So let's say if we have a CMOS, which has a 2000 nanometer thick membrane made of LPCVD silicon nitride, and then you have the passivation layers between the top and bottom aluminum electrodes in order to avoid short circuiting when they come next to each other in collapse. So cavity is about 250 nanometers. So for these dimensions, if I put this in these vertical and lateral dimensions into the circuit model I've shown, what I get is at a resonance of about 7 megahertz, and the quality factor is about 4.5 at the resonance K of 0.72. The first advantage of using the circuit is that all the physical quantities of interest like resonance frequency, mechanical quality factor, the bandwidth, each and everything can be found out in terms of the circuit elements. For example, the mechanical quality factor can be written as such in terms of the mass of the membrane and the reactive loading, or the mass of the acoustic medium you add it to the inductance. And for a series RLC circuit, you can find the mechanical quality factor as such. So, I mean, you can analytically, you can see as a function of the resonance Ka, K is the wave number at resonance, A is the aperture size. If you put those dimensions and material properties, you find out that, okay, at 7 megahertz, it's about 4.5. And just to show you how accurate it is, if you construct a, let's say, a 2D axisymmetric model having the same dimensions, so you can see there are two aluminum electrodes, and then there's a 250 nanometers gap in between. And if you model the acoustic port correctly, having a perfectly matching layer or enforce absorbing boundary condition to ensure spherical radiation condition, that the acoustic port is properly modeled, then you don't see much of a difference in the bandwidth, simulated bandwidth, or the frequency. So all the parameters of interest like impedance level, frequency, and bandwidth, they match perfectly well. So circuits can be said to work at the accuracy level of FAMS. Also, the other things like obtaining the transfer function. So if you have, for example, incoming echo, there is a certain pressure on the acoustic port that is going to be interpreted in terms of the receive voltage signal. So the volts per Pascal is the receive sensitivity. So this is for a single cell biased at 200 volts, and you have this about 35 dBs reference to 1 millivolt per kilopascals. Now the interesting thing are that what happens when it comes to the arrays. So for arrays, we have these single cells which becomes the building blocks of the array, and we have a large number of these cells terminated into a large impedance matrix. So this impedance matrix is what accounts for the mutual coupling between the individual CMOS cells or elements. So CMOS cells in the medium are not only coupled to the medium only, but they are also coupled to each other, because the sound generated by, let's say, one of the cells as a transmitter is also affected. It's also going to push the other neighboring cells, and it's going to see the loading due to that. So that's a secondary phenomena which is taken into account. So to give you an idea how this Z matrix is, let's consider 3 cells which are linearly placed, and let's say a harmonic signal is applied, and at a certain point in time, you see the membranes are supposed to be pulled up, but the center membrane goes down. But when the excitation is gone, it's pulled up. So with respect to the phase of this excitation, the center cell sees a negative resistance. Okay, when the excitation is applied and it is supposed to be pulled up, it goes down. When it's not there, it goes up. So it's out of phase. So it sort of sees a negative radiation resistance, which is very evident in the real part of the mutual coupling, let's say, real part of the mutual radiation impedance. You see that real part can go negative, and this is what it means. So some of the cells can see a negative radiation resistance because not all the energy is going to be coupled to the medium because of the vibrating membrane. Some of this goes into the pushing each other or the neighboring cells if the pitch is smaller compared to the wavelength of operation. I'll just explain this phenomena, what effect it has on the bandwidth of CMAT. So let's start with two cells, which are the acoustic ports you can see are coupled through the impedance matrix. And according to reciprocity, how cell 1 is affected by cell 2 is the same as how cell 2 is affected by cell 1. Okay, so that's a symmetric matrix. So Z12 and Z21 are similar, and the on-diagonal elements are the coupling impedance of these individual cells to the medium. So if you have two cells and two cell element separated by a certain pitch, let's say D, which is less than half wavelength, then you see by acoustic reciprocity, the bandwidth, the electrical impedance, the frequency, bandwidth, everything, impedance level is the same. So cell 1, what cell 1 experiences is the same as cell 2, what cell 2 experiences due to cell 1. So the acoustic loading due to the medium and due to the cell 1 pushing the medium around cell 2 is the same as what cell 1 experiences. Okay, so but if you have, let's say, a single cell reference for a single cell, which I've been showing before, if you compare this with two cell element, if they are driven electrically in parallel, you see the effect of loading. So the bandwidth does increases at the same operating frequency. So let's consider three cells. And again, once again, the on-diagonal elements are the coupling elements of the matrix. I mean, the coupling to the medium. And the off-diagonal elements are the mutual coupling. So mutual coupled elements. And what happens is that what cell 1 is going to experience is the same as what cell 3 is going to experience due to 2 and cell 1. So they are the same according to reciprocity. It's a symmetric matrix. But what happens with cell 2 is that it sees a different pitch. I mean, the way the medium is moving around over how cell 3 and cell 1 are pushing cell 2 is different as compared to what happens with cell 1 and cell 3. So you see a very narrow band response, a very sharp, very narrow band response around the same frequency from cell 2. And this effect continues. I mean, you can interpret this time for number of cells. For example, these are 10 cells linearly placed at pitches less than half wavelength, and still you can see how cell 1 experiences the effect not only to the self-coupling to the medium, but due to the mutual coupling of all the cells and the load that it sees due to all the cells which are vibrating at the same time or due to the excitation. They are electrically connected in parallel. So what cell 1 is going to experience is going to be the same as cell 10. So cell 1 is the same as cell 10. These are individual cell electrical impedances, but if I combine them into one element, so as a reference, if I compare this with a single cell, then when I have two cells, the bandwidth increases. The bandwidth further increases with cell 3, but I have a sort of, let's say, a spurious frequency dip, which occurs around 6 megahertz. And this tends to limit the bandwidth. But this problem can be, in this particular 1D array, can be alleviated if you increase the number of cells. So you don't have this problem for a larger number of cells. So just to collect the results, if you go from cell 1 to, let's say, increase the number of cells to 10, so that you see the bandwidth increases twofold, but twice, so it's 1.2 goes to 2.4 approximately. But that's not the case when you go from you increase the number of cells in an element from 10 to 50, then the increase is very subtle, 2.51. And just to mention again, this is not the periodic boundary condition, or we are not simulating let's say a single periodic element from an infinitely large array as done in FAMS. we are simulating a full-blown array in a very short period of time owing to the analytic nature of this matrix and the circuit elements. So we are taking the effect of all the neighboring CMOS cell elements coupled to one another, you know. So simulation time is much shorter and the results are much accurate. But when it comes to simulating a CMOT in this DHUT configuration with the resonant backing, we need to consider the substrate impedance. So this substrate is introduced. So these elements are introduced as a low frequency stack, and how CMOT looks at this impedance and how it reconfigures it depends on the magnitude of the substrate impedance. So to explain how these substrate can be derived in terms of the low frequency stack, well, looking into the layers, we start with the epoxy loaded matching layer. Then we have PZT, dematching layer, and backing. So for PZT, we have a 3-port standard Mason model, 3-port electromechanical network, with the C0 being the clamped CMOT capacitance. And then you have this the impedance of the PZT layer. C0 is the clamped capacitance and is the electromechanical turns ratios. F and V, they represent the mechanical force and velocity at the resonator front and back surface. So since there are the other layers, you'll have a finite piece of transmission line segments. So there are 2 ports transmission line segments, passive segments, which are connected to each other. And this is the impedance which is seen by the CMOT at its backing. So it's not rigid; it's a resonant backing. So if you compute the magnitude response of this low frequency stack, you see there are many peaks occurring at distinct frequency points, and at those peaks, the magnitude is infinitely large, at which the CMOT does not reconfigure its frequency response at all because ZBPS is open circuit. But during this, I mean, in the frequency ranges where the magnitude is very small, it's the point where is the frequency range where the CMOT sees ZB as a soft backing, and then it reconfigures its response. So if this impedance is introduced right across the transduction force in the model, and that's how it looks. I mean, these are the transfer functions. So on the left you see volts per Pascal, on the right you see amps per Pascals. Both are equivalent. I mean, the ratio of this is the impedance, but depends on the choice of interfacing electronics. If you use a voltage preamplifier, then it's volts per Pascal, or a transmitter amplifier, then it's amps per Pascal. So for a preamplifier, if you have to use a preamplifier with a CMOT, then you look at the dB volt per Pascal, and what you see is that within this range of where the impedance is small, the CMOT shows 2 notches over here, which is due to the underlying PZT stack. And then there are some other peaks at high frequencies, which are again due to the point in frequencies where the when you have the soft backing. Okay, so this is the effect of actually the coupling that we have from the active PZT resonator. If PZT is silent, if it is passive, you're not it's not an active transmitter, then you don't have this. It's again if the D hat is with the passive PZT layer, it's a very nice and clean response, very wide bandwidth. But when the PZT is active, then yes, you start looking at this coupling. So just to differentiate between what happens once you introduce the low frequency stack to the pure CMOT elements. So these are that's the multiple CMOT cells placed together, connected electrically in parallel. So for example, you go on from increasing the number of cells in one element from single cell to, let's say, 40 cells. As you go on, of course, the loading is increasing, so it becomes very wideband. But if you have less number of cells, the effect of mutual crosstalk due to this matrix is there. This predominantly limits the bandwidth, but it's not the case if you have a large number of cells. And usually, when you have a large closely packed large number of cells, you don't have this problem, and it's wideband. But if you have a PZT backing, then despite of the fact that you have a large number of cells, you still see these 2 notches around 4.5 megahertz, which is the operating frequency of PZT, and that coupling holds even for a large number of cells, and you still have this peak, and the bandwidth you can see is limited due to this coupling from the low frequency stack. To show you what we are looking at now is that we have this fabricated XA1 chip from Aculab in Italy, and you can see that the elevation is a 13.2 mm chip, and it has 60 bond pads, and it's a 2D array actually. But what we intend to do is to use this as a 1D array. So if, for example, if we connect one bond pad, this is one bond pad. You see the cells, they are connected as such that for each element there are 4 cells which are separated by 110 microns, and there are about 120 such elements, making a total of 480 cells against each bond pad. So if I just showed you quickly the simulation of these 480 cells combined on a PZT stack, what we are going to experience in practice based on the predictions of the circuit models, and I give the same dimensional parameters as I've shown before for a single cell. Then for a 50 micrometer aperture size membrane diameter, which is about quarter wavelength at 8 megahertz, the response is very clean. The transfer function is very nice because it's a single cell. You don't have much of bandwidth. But when you increase the, let's say, include more cells, like let's say 4 cells, of course the bandwidth goes down. The bandwidth increases, the impedance level goes down. The capacitance increases because you have more cells now, so you have a bigger capacitor. The bandwidth goes up in the transfer function, can be seen. It's very nice, very clean. Then if you simulate one wavelength long array, then you start looking at, because the number of cells are smaller, you again see this sort of spurious resonance, a problem at around 7 megahertz. So otherwise the bandwidth is very nice, very clean. As you go on increasing the number of cells, the bandwidth still increases a bit further for 2.7 wavelengths long, but the stop bandwidth starts appearing around 28 megahertz. And then if you consider 5.5 wavelengths long an array, 5.5 wavelengths long array, then this phenomena, which is due to the mutual coupling between CMAT element, is too little. I mean, it's not much. So, but the stop bandwidth becomes prominent. So this occurs at 28 megahertz, and in between the response is very, very smooth, very nice. For 80 cells, for 20 such elements, 2 cross 2 elements, you don't have any such problem at the operating frequency. Well, the stop bandwidth is still there. So compared to the single cell, it's very wide bandwidth. Now, this is again the same picture as I've shown before. If we have large number of cells, then but when you have this on the resonant backing on the PZT, then despite the number of cells, you still have these the coupling from the low frequency stack to the high frequency stack, and this effect limits the bandwidth for image. So one way is to use the circuit model is to design, if there's look out if there is an appropriate design for the CMOS array. And as I've said, that these circuits can be used to design the CMOS. So for example, if I go for a smaller aperture size, instead of going for quarter wavelength, let's go for lambda by 8 element single cell. Then to keep the same resonance frequency, you have to use a lighter membrane as well. So, but what happens is that as you go on increasing the number of sections, increasing the number of cells and elements, the cross coupling and the crosstalk between the CMAT elements, it becomes quite prominent, and it doesn't go away with increasing number of cells. If you use small cells to pack large number of CMAT elements, it doesn't go away, and it severely limits the bandwidth for very large number of cells. Even even if you have like 80 cells over here, this is what limits the CMAT bandwidth. As compared to that, if you have very large CMAT element diameter, then the bandwidth is smaller. Okay, if you have a smaller aperture size, then you have this cross coupling. But if you have the in between the diameter is about quarter wavelength, and the pitch is about half wavelength, less than that, and the membrane thickness is about 2 microns. Then you have a very good response. I mean, the peak sensitivity is better in all the other cases for quarter wavelength diameter membranes. You see that it's higher than both of these cases. The frequency doesn't shift because the frequency shifts for smaller aperture sizes a little bit to left and then right for the larger aperture sizes. Smaller aperture sizes are more affected by the mutual crosstalk, while the larger aperture sizes are not much affected, but the stop bandwidth is less, much less as compared to 28 megahertz. So in order to use the circuit models to predict the behavior and to simulate the entire array, you can predict the response, and you can design a CMAT array for very wide band response and for the given received sensitivity. I mean, that's how you use the circuit models. So you use the circuit models to evaluate what kind of membrane thickness and aperture sizes you will require to fabricate for the given, to match the given bandwidth and the received sensitivity. So the concluding remarks are that we have an equivalent circuit model for DHUD that is proposed here, which is capable of simulating large CMOS cells with resonant packing. The simulation time and the memory requirements are much shorter, less compared to FEMs, because of the analytic nature of these models, and they are suitable for analyzing the physics of hybrid transducer, taking into account the nonlinear effects like coupling within CMOS elements and coupling between the low frequency and high frequency stacks. And these models are also suitable for design optimization. As I've said, they can be used to design for a given to find out the given parameters of CMOS which match the required bandwidth and the received performance. So the current project involves bonding the CMOS chip as I've shown on the PZT layer, and then characterizing the acoustic performance of hybrid architecture. Yeah, that's about it. Thank you for listening.